All right, M.1. So we are starting today to talk about matrices. So you should have already watched the little Khan Academy, just a couple minute long Khan Academy video on matrices, where he talks about how matrices are like groups of numbers. So we could have a matrix that looks like 1, -10, 4, 3, 2, 0. I made that up. This is a matrix. And we normally say that they are rows by column. So a matrix will have a dimension. The number of rows is 1, 2, 3. And the number of columns is 1, 2. So we would say that this is a 3 by 2 matrix, just like this. And that's going to matter because there are times when matrices have to have the same dimension in order for you to do operations on them. For instance, you have to have the same size of matrix to add or subtract matrices. So one more thing that I wanted to add on to what he said is that if you're looking for just one part of a matrix, like say I just want to talk about this 3 right there, I would refer to this. Normally we would give our matrix a name. Like I would say that this is matrix J. I'd say J equals this matrix. So then I would refer to this spot. This is one element. So each one of these numbers is an element of the matrix. And this is in the second row. So it's in the second row, and it's in the second column. And that overlap is where that 3 is. So second row, second column. So we would normally refer to that as the element lowercase j, so this is lowercase of the capital letter that it's named after, lowercase j, 2, 2. So it kind of looks like J22, but that 2, the first 2 means the row, the second 2 means the column. So if I asked you what J31 is, that'd be the third row. So third row is down here. And then the first column. So third row, first column would be this 2 where those overlapped. So that would be just the number 2. And that will be important also. But we're going to start talking about add, subtract, and scalar multiply matrices. Basically, add, subtract, scalar multiply work just like you would expect them to. So if I have that matrix J that we just barely talked about, and if I come up with a new matrix, we'll call it Q, and matrix Q looks like -10, 0, 0, 1, 3, 9. Just like that. So this is also a 3 by 2 matrix. I can add J plus Q. I can add these matrices, and it would just become like the resultant matrix will still be a 3 by 2 matrix. And I'm just going to add them in the same component. So like the top left corner, I'll add the 1. I'm going to make a little circle here and move that around. So I would add this 1, this element 1, their 1, 1 element, to the -10. And that would get me, so I'd have 1 plus -10 would be -9. And in the top right corner, I have -10 plus 0 is still -10. And then in this spot right here, I have 4 plus 0, so that's 4. Next to that, I have 3 plus 1 is 4. 2 plus 3 is 5. And 0 plus 9 is 9. So there's my answer. Each one of the elements is just the like associated elements added together. And you could do the same thing if I wanted to do like Q minus J. I would just subtract each of the elements. So Q minus J, notice I'm starting with Q, so that'd be -10 minus 1 would be -11. 0 minus -10 would be +10. 0 minus 4 would be -4. 1 minus 3 would be -2. 3 minus 2 would be 1. And then in the bottom right-hand corner, 9 minus 0 would be 9. And that would be Q minus J. The last thing is that scalar multiply. So that means that I'm going to multiply like on the outside as a number. So let's say I wanted to do -2Q. I wanted that. That's going to be -2 times this whole matrix. And just like with the vectors that we already talked about, basically that -2 is just going to get distributed into every single element in here. So we're going to distribute that -2, multiply it 6 times. That looks like one of those fireworks that looks like a, I don't know. Anyway, negative 2 times negative 10 for that top left corner is going to be positive 20. Negative 2 times 0 is still 0. Negative 2 times 0 is still 0. Negative 2 times 1 is negative 2. And then negative 2 times 3 is negative 6. Negative 2 times 9 is negative 18. Nice. Okay, a couple of things to mention. For adding and subtracting, so what we were doing right here in the middle, the matrices have to be the same dimension. You cannot add matrices, like it doesn't make sense to add a matrix that was 2 by 2 to a matrix that's like 5 by 1. Like, then what do I add this guy to? Question mark. I don't know what I would add him to. Or what do I add this guy to? Because there's nothing over here in the second column. So they have to have the same dimension. Or else it's just undefined. Have to have the same dimension. Just like in our regular numbers we've been dealing with for most of our life, we have the number 0. Like when I add 5 plus 0, then it just stays 5. There's something equivalent to it in matrix form, which would be whatever size matrix I'm dealing with. So say I have some matrix that's 2 by 2, so it's like A, B, C, D, those are some numbers. I could just add the 0 matrix to it that's full of zeros, and it would just stay that original A, B, C, D. So that's kind of the equivalent of like 0 in our numbers is like a 0 matrix, just a matrix filled with zeros. And I think that's about it for add, subtract, scalar, multiply. So, happy scaling.